Okay, last chapter we talked about objects that were being launched perfectly horizontal. Now we did say that there was going to be a vertical motion to it, but we said that it was only going to have that vertical motion after it left that horizontal plane, for example, a table. Well, what we're going to do is we're going to be looking today at objects that have both vertical and horizontal motion. For example, if you take a golf ball, and we take that golf ball and we hit it, of course you know that it's going to go up and it's also going to go forward. You know that it's going to go forward some x distance, and you also know that it's going to rise into the air. So we're also going to have some y component. Now again, when we go ahead and look at this parabola and we look at this highest point here, really what we can do is we can say, okay, there is a time up and there is a time down. Now, if this object is going to start and land at exactly the same point, a couple of things that we can say is the time up is going to be equal to the time down. Some other things that we can say is we can say VXF is going to be equal to VXI, and VYF is going to be equal to VYI. Now realize it is going to be falling, so therefore that VYF is going to be negative. Now again, if we say that it takes off at 10 meters per second going up, it's going to land at negative 10 meters per second. So again, that magnitude 10 is going to be exactly the same. Now the equation for time. Time is going to be equal to negative 2 VYI divided by G. So what we're saying is negative 2 multiplied by the initial vertical velocity divided by gravity will equal the time. Now that's going to be the total time. That's going to be from start to finish. And the other equation that we're going to end up using is going to be y is going to be equal to VYIT plus 1/2 GT squared. Again, y is going to equal your height. VYI is that initial vertical velocity. Time, of course, is t. And g, of course, gravity, and then, of course, time squared. Okay, to again get this equation to work, make sure that you are using the negative value for gravity to make sure that everything is going to work. Now, you might be asking yourself, well, how do I know what these values are for Vx and Vy? So a couple more equations that I need to put on the board is Vyi is going to be equal to the sine of theta multiplied by the initial velocity. Now what I mean is we're going to look at this portion right here at what it takes off at. And again, sine is always going to be y, and we're going to take the initial velocity and then multiply it by that angle at which it is launched at. Vxi is going to be equal to the cosine of theta multiplied by Vi, or that initial. So again, what we're saying is there is going to be a Vx component, there is going to be a Vy component. And again, when you look at that first sample problem I have here, it says a golf ball is hit from the ground with a velocity of 100 meters per second at an angle of 12 degrees. And therefore you should be able to see that we're going to be able to get ourselves, or give ourselves, an initial vertical and an initial horizontal velocity. So let's go ahead and start this sample problem. Okay, so the information I have Vi is equal to 100 meters per second. I have theta is equal to 12 degrees. A says find the maximum height the ball reached, and B says find the range of the ball. So what we're really trying to do here is we're trying to find x and we're trying to find y. Now again, looking at b, x is going to be equal to vxt. Again, we're going to be using a lot of the same equations that we used last section, or that last section when we talked about horizontal motion. So let's go ahead and look here. Okay, Vx, okay, because we're going to end up needing a Vxi. So we said Vxi is going to be equal to the cosine of 12 degrees multiplied by that initial speed, 100 meters per second. And Vyi is going to be equal to the sine of 12 degrees, also multiplied by 100 seconds. So let me go ahead and come back here. Let's get out of this. I need to bring up my calculator here. And when I go ahead and bring up my calculator, there it is, and I need to go back into my Interwrite board. Okay, so what we're going to do is we're going to take 100 multiplied by the cosine of 12, and I'm going to find out that the initial horizontal velocity is going to be 84.38. So 84.38 meters per second. Okay, let's go back and let's look at our vertical speed. And again, we're just going to back up and get rid of cosine, and we'll change that into sine. Go ahead and hit enter. And, got a problem here. I notice that I am in radians, not degrees. So let me go ahead and get that back into degrees, and we'll enter that again. Okay, so 20.79 is this one, and I better go back and check my horizontal. We'll change that one to cosine, and we get 97.81. 97.81. Okay, 97.81 meters per second. So what we have is we have a horizontal speed and we have a vertical speed. So again, this object was launched basically at that angle, but what we're saying is we have a Vx and we have a Vy. So again, it says find the maximum height that ball reached. And again, the equation I have up here, y is going to be equal to Vyit plus 1/2 gt squared. So let's go ahead and look at that. Y is going to be equal to Vyi. Okay, that says 20.79. Okay, so now the problem is we need to figure out time. Well, time, if you remember that equation that I had up there, time is going to be equal to -2 Vyi, which is that 20.79, divided by gravity, which was -9.81. So let's go ahead and plug that in. -2 multiplied by 20.79 divided by gravity, -9.81. Close my parentheses off there, and I go ahead and enter, and we're going to find out that the time is going to be equal to 4.24 seconds. 4.24 seconds. Now that 4.24 seconds, that is to go from here all the way over to here. So what we're saying is, if we want to figure out how high this ball went, we're going to have to use half the time. And to use half the time, basically what we're going to do is we're going to divide that by 2. So you're going to find out that there's going to be 2.12 seconds up and 2.12 seconds down. So what I can do now is plug that in here. 2.12 seconds. Plus, okay, again, that equation was VYIT plus 1/2 gravity, negative 9.81, multiplied by 2.12 squared. So if we go ahead and plug that into my calculator, we're going to have 20.79 multiplied by 2.12 plus 1/2, okay, or 0.5, times negative 9.81 times 2.12 squared. If I go ahead and hit enter, what we're going to figure out is the ball rose 22.03 meters into the air. So 22.03 meters. Okay, so that answers part A. Part B says find the range of the ball. Now here's the thing. The ball was in the air for a total of 4.24 seconds. So the thing is, that ball went 2.12 to get to there, the halfway point, and it also then went 2.12. So we're going to use the total time when we solve for x. So x is going to be equal to VXI t. Okay? So we found out that the initial horizontal speed was 97.81 meters per second. We're going to use the total time there, 4.24 seconds. And when I run that through my calculator, I'm going to find out that 97.81 multiplied by 4.24, and when I hit enter, the range of the ball is going to be 414.71 meters. So there will be our two values for horizontal and vertical heights of this ball. Okay, let's look at our second sample problem. It says a football player throws a football with an initial velocity of 12.7 meters per second. So again, here's going to be our VI. It says he throws it at an angle of 62 degrees. So there will be our theta. And this one says how long was the ball in the air. So again, we're going to try and find height or time here. But it says here the ball was released 1.5 meters above the ground. So really this is what we have for a picture. Okay? So we have this portion right here where the ball comes across. But the thing is, we have it actually falling an extra 1.5 meters. The time that we find is going to be to go from here to here. Okay? It won't be including that 1.5. So we have to figure out how to find that time that it's going to take to fall that additional 1.5 meters. Well, let's go ahead and use the equations that we have right now. Okay? So I'm going to go ahead and figure out VYI. VYI is going to be equal to the sine of 62 degrees multiplied by that initial 12.7 meters per second. So 12.7 multiplied by sine of 62 will equal. So 11.21 meters per second was the initial vertical velocity. Well, let's go ahead and figure out time. Time is going to be equal to negative 2 VYI and G. Okay? So what I'm going to do is I'm just going to figure out how much time it's going to take to go and rise and then fall back to that same spot, because we're going to be able to use that information. So time, negative 2, VYI, 11.21 meters per second, divided by gravity, negative 9.81 meters per second squared. So, negative 2 multiplied by 11.21 divided by gravity, negative 9.81. And I find out that the time is 2.29 seconds. Now again, that 2.29 seconds, that's going to be to go from here all the way over to here. But what we need to do is again, we said that to get to that highest point, it's going to be half of your time. So basically what we're saying is it's going to be 1.145 to go up. Okay, so the time up is going to be equal to 1.145 seconds. Time down, well, that's our question mark. That's what we don't know right now. Okay? Now, one piece of information that we'll be able to use is, let's find out how far that ball went up. Because if we figure out how far it is to get up to there, we know that it's going to fall that same distance. The ball's going to go up, but the ball's going to come back down that extra 1.5. So we can figure out that y to fall. So again, let's go ahead and look at this. Y is equal to VYI, so 11.21 meters per second, multiplied by half the time, so we're going to use the 1.145 seconds, plus 1/2 G negative 9.81, and then 1.145 squared. So let's go ahead and figure out the exact, or how high that ball initially went into the air. There we go. Okay, so 11.21 multiplied by 1.145 plus 1/2 negative 9.81 times 1.145 squared, and we'll get an answer of the ball rose about 6.40 meters. 6.40 meters up. So here's the thing. The y down is going to be the same distance, 6.40 meters, plus that additional 1.5 meters from the arm to the ground. So it's going to fall a grand total of 7.90 meters. Well, let's go ahead and come back to our equation. Y is equal to VYT plus 1/2 GT squared. Again, think of this. At our highest point, we're going to have an initial velocity that is equal to 0. At your highest point, for a split second, that ball begins, or that ball stops. So we can get rid of that VYT. So I can go ahead and plug in. The distance it's going to fall is negative 7.90 meters, is equal to 1/2 negative 9.81 time squared. Rearranging, we're going to go 2 multiplied by negative 7.90. We're going to divide it by negative 9.81. That will equal t squared. And to get rid of the squared, we'll go ahead and actually take the square root of it. So 2 multiplied by negative 7.90 divided by negative 9.81. Enter second square root, second answer, and we're going to find out that it's going to take 1.2 seconds to fall. So we've got time up. We said it was 1.145 seconds. We said time down was equal to 1.26 seconds. So the grand total time, 5, 0, carry the 1, 4, 2.405 seconds. Looking at a problem that has different heights. Let's go ahead and look at our last sample problem here. It says a softball is hit at 22 meters per second at an angle of 60 degrees with the horizontal. It says immediately the center fielder runs in at 3.75 meters per second, catches the ball at the same height that was hit. What was the original distance between the batter and the outfielder? So what we have is we have a ball that is being hit and coming back down to that same height. Now this problem also says there is an outfielder that is right here. And it says that outfielder runs in. So the question is, what is this original distance between the batter and the outfielder? So what we're saying is, we've got an X for the ball, and we've got an X for the outfielder. So I need to solve two X or horizontal distance equations. Well, again, just like what we've been doing, we've solved for Vxi and we've solved for Vyi. So Vxi is going to be equal to the cosine of 60 degrees. Clean that up a little bit. Cosine of 60 degrees multiplied by 22. We're going to have sine of 60 degrees also multiplied by 22. So let's go ahead and figure out these numbers here. So 22 multiplied by cosine of 60. That'll equal 11. Let's find our y. Bring that back. We'll go sine there. Now it's going to be 19.05. So we've got 11 and 19.05. So let's go ahead and let's use the equation for time that we talked about earlier. Let's find out how long that ball is going to be in the air before it's caught. So we said that -2 Vyi 19.05 meters per second divided by gravity -9.81 meters per second squared. So the ball is going to be in the air for 2 times, -2 times 19.05 divided by gravity, -9.81. We find out that ball's going to be in the air for 3.88 seconds. Okay, that makes this pretty easy now. So let's go ahead and let's find the range of the ball. Okay, the range of the ball is going to be equal to the initial horizontal speed of the ball. And the initial horizontal speed of the ball will be that one right there. So 11 meters per second multiplied by time, 3.88. So we're going to find out that the ball is going to travel 11 times 3.88. The ball is going to travel 42.68 meters. 42.68 meters. Now, at that same time that ball was hit, that outfielder took off running. Okay, so we need to find the range of that outfielder. And it says the outfielder ran at 3.75 meters per second. They ran as long as that ball was in the air, so they ran for 3.88 seconds. And when I do that, I find out that the outfielder, 3.75, multiplied by that same time that they ran, or the same time that ball was in the air, 3.88. So that outfielder is going to run 14.55 meters. We're going to add those together to figure out this total distance from initial start of outfielder to initial start of that ball. So we're going to have a 3, carry the 1, 6 and 5 is 11, and the 1 is 2, 2, 4, 6, 7, 57.23 meters was the original distance between the outfielder and the batter.